Alright guys, we are technically on video number 8 due to time. I've skipped 7, I'm just sort of focusing on the more tougher parts. So video number 8 is simple harmonic motion, without a doubt in every single HSC exam and extremely important. So let's start. I've got just some information here, a bit of a summary, an easy question to expect in the multiple choice and what to expect in more tougher questions, okay? So this tougher question's toward the back of the paper, so we'll work through it together. Basically, simple harmonic motion is anything that's oscillating, so moving. We call it straight line motion, but basically it's sort of centered around the straight line and it's moving up and down that or in some sort of oscillation. So tree graphs of sine and cos are good examples of that. But basically, if we're looking at on a straight line, if we're looking at where it is, okay, so we've got 0 being its displacement, okay, so it's starting at 0, and basically what it's doing is it's coming up, hitting, and it just keeps going. That's what it looks like in a straight line form, okay? So, thinking about this, what is happening in terms of our velocity, so our speed, and our acceleration if this particle is just moving? Imagine running, it's a bit hard, but imagine having a rubber band around your finger and your other finger is pulling it out to one side and then it moves it back to, your finger moves back to the center to meet your other finger and pulls it back out the other side. Maybe, yeah, try and imagine that. So it's kind of like the same idea. Now think about the speed you're traveling, okay? So your speed stops at either end, okay? So basically what happens is when this particle or whatever it is moving, it's going up to the end, it stops, so its speed is 0 at the end points, okay? And turns back around. Its speed is a maximum, okay, when it's in the middle, okay? Now let's think about its its acceleration. The acceleration is, the force of the speed, in other words. So think about this rubber band. Its most force, its maximum force is when the further you pull it away, so like the end points. So that's why we have that here, our second derivative, which is our acceleration, is a maximum at the end points. And obviously when your two fingers meet back in the middle, there's no tension on the rubber band, so that force is 0. The other thing I'll mention is A and negative A, so that's like your amplitude. Same idea as like a tree graph, as we call the amplitude what it stretches up and down to, okay? So it's the distance from the center. Alright, some formulas to know and remember. Again, I did my HSC not using the reference sheet, so I don't know the reference sheet, so check to see what formulas you do get on it. I think from memory possibly you do get just this one, so I guess remember the others. We'll definitely remember the others before tomorrow. But basically I've written the formula there and I've written in blue what it is. So you've got your displacement at the top there. Now most of the time the questions involve cos. They don't generally involve much sine. They can involve sine, but I don't know, most of the questions involve cos. And so we represent, in simple harmonic motion, we represent the displacement in this form, okay? Where we have A as our amplitude, but it should look somewhat familiar to you when we think about trig and trig graphs, I guess. Now, there is a proof to it, and it's something to have a look at, but eventually you can prove that if you differentiate and then obviously square it, because it's squared, you can get to this equation here. Most questions, though, don't test your ability to proof. In fact, I don't think I've seen a HSC question that does that. So it's okay, I think, in my opinion, if you do just remember that rather than just the proof to get it. Now, again, here, A, noting A is your amplitude, okay? So then we have, if we did differentiate that again, we would get your acceleration formula, okay? The idea is, though, these proofs are a bit long-winded, so have a look at how to do them. It's not as simple as just differentiating. But basically, that formula there is important, and you get given it most of the time in the question, because to prove something moves in simple harmonic motion, you just show that the second derivative, or the acceleration, can be written in that form. So, in other words, if you differentiate twice, you should be able to factorize out some constant out the front, and in brackets have x minusing some other value, and that value might be 0. So if you can prove that acceleration of any journey of any particle can be written in that form, it moves in simple harmonic motion. And finally, t, which is represented as the period, or in other words, the time taken for a full oscillation. Okay, and f is our frequency, so it's the number of oscillations per second. So let's jump straight in. We've got an extension, a multiple choice question here from extension 1 2012, and it was apparently done quite poorly. The state average was only 69%, and my particular school average was not great for it last year either. So let's have a look at this. It tells us the velocity is given in that form, and straight away you're thinking in your memory, that's the velocity formula. It says what is the amplitude and the period of the motion. So instantly, if you know your formula well, you know that a squared is this term here, is the 9. Okay, so straight away, and it doesn't hurt to just show the marker, you know that a squared is 9, although it's multiple choice, but if it wasn't multiple choice. Then it's about finding t. Okay, so again, t is your period of this oscillation, so 2 pi on n, and noticing n, okay, thinking about where n is in my formula, n is the square root of 16, so 2 pi on 4 gives me pi on 2, and there's my answer, A. Really straightforward if you know your stuff. Okay, not so straightforward. Let's look at this question. Common. I've seen it a few times asked in HSC, where you kind of have to do a bit of a proof to start with. The equation of motion for a particle is moving in simple harmonic motion if it's given by that. Yep, we knew that. And remember, that's the exact same thing as minus n squared out the front of x minus c, but just c is 0. Okay, so it is something we are familiar with. Okay, show that the square of the velocity of the particle is given by this. So again, here we have the proof going back the other way though. So they're giving us acceleration. This is the more common one. Rather than proving downwards, proving upwards. And learn it and know it, because I have seen this asked a couple of times. Alright, so let's have a look. I'm just going to put my answer out and then I can talk about it. Okay, so hopefully this will make some sense. But basically we are told that we are given this, okay? So the second derivative, for our acceleration, is negative n squared. And we have to prove that it can be also written as v squared equals. So I'm thinking, all right, how can I get in terms of x? So this is using your extension 1 applications topic. In terms of x, I can't just, integrate both sides. I have to get to my velocity by replacing my acceleration with another acceleration format. Okay, hopefully that rings a bell. Remember, acceleration has a lot of different ways we can represent it, and basically we pick the form of acceleration that is in terms of v, because we want the one where we can rearrange for v equals. So all I've done here is I've said, okay, the acceleration is the same thing as this, and that's just another form of writing acceleration. So then I've said, okay, if I integrate both sides now, so all of a sudden now I have a v involved, which is what I wanted, because this has v squared equals. If I integrate both sides, d on dx is saying the derivative, so integral and derivative will cancel each other out, so I'm left with a half v squared, and I have the integral of negative n squared x. Remember, where n is just some value, some number. When I integrate, I add 1 to the power of x, because remember I'm integrating in terms of x. N is just some number. add 1 to the power and divide by it. So I get this term here plus c. With my 2's on the bottom, they can get rid of each other. Okay, so think of just multiplying everything by 2. And I get this here. Now my problem is with this, I've got c. And I don't know what c is. So I need to find it. So I think of some values that I know. And what do I know from my straight line? That when I'm at A, for instance, I knew my velocity is 0. So that's like a point I can substitute in to find my c value. And so I do. When I sub that in, I get a value that c is equal to this. And replacing that for c in my velocity squared formula gives me this. And all I've done here is factorized out my n squared. And there's my proof completed. Okay, so it's not too difficult. I guess the hardest part is remembering to replace your acceleration d2 x on dt squared with another version of acceleration written in terms of v. Okay, so if I get rid of all this, let's look at part 2. So this part just wants you to find the maximum speed. Thinking back up here to our straight line with a bit more information on it, when is our speed a maximum? When x equals 0. Okay, so we have now a formula for our speed, or our velocity I should say, and we just need to know when v squared equals n squared outside of a squared minus x squared. We know there is a maximum when x equals 0, because the maximum velocity occurs at 0. So all we're going to do now is substitute that in. And I can just leave it at that. So I can write that as just n squared a squared, and that's what v squared is. So v is just na. Alright, so I don't have any values on this question, and that's what people find more difficult. So again, a reason why I chose to do this question, because you might have actual values, and this, your v max would be a number coming out of it, but this one doesn't. So it can apply to any question really. Okay, so then part 3. Oh, one thing I just wanted to note there is, notice how part 1 was a proof question, which means if you got to part 2 and you had no idea what to do, you're going to use what you just proved, because there's no other reason they make things a proof question unless you have to use it on the very next question. Okay, part 3. Find the maximum acceleration of the particle. So again, think back up here. Where is the acceleration a maximum? Acceleration is a maximum at its endpoints. Okay. So I would tell the marker again that my acceleration has a maximum at x equals plus or minus a. Now it's just about finding, okay, well, what do I have for a formula in terms of the acceleration? And that's the one they gave us here to start with. Okay, so I'm just going to be subbing in my a value into that. And that's what I end up with, subbing it in. It's really straightforward. It's just they're testing that you just know your stuff. Okay, next part. We have to... Oh, that was part 3. So part 4, the particle is initially at the origin. Write down a formula for x as a function of t, and hence find the first time that the particle's speed is half its maximum. Okay, so straight away, we know that our displacement, I've written here, is generally written in this form here. I did mention before though, it's sometimes and not often written in this form. So the idea is we aren't sure which one. So basically it's most of the time it's the cos formula, but it could be sine. So you have to understand which one to use, and the understanding comes from exactly this piece of information here. The particle is initially at the origin. So you think to yourself, okay, well, if the particle's displacement is initially at the origin, which one would it be, sine or cos? And straight away, it's obviously this sine graph, okay? It's cos doesn't start at 0, it starts at 1, so it's definitely going to be our sine displacement. So that's the first thing I want to be writing down. And it wants to know, so there's our formula, find the particle speed when it's half its maximum. So basically I want to differentiate it because I also need its speed. So let's have a look. Okay, so this is our displacement formula for sine. It's the exact same thing as the cos one, but we just write sine. Now if it's initially at the origin, then we know that it's not going to be moved sideways, which is what alpha does, okay? Alpha picks up the tree graph and moves it sideways. So basically that's what we have there. So now I have a formula that is x in terms of t. So to get velocity, this goes back to 2-unit calculus, I can just differentiate. And when I differentiate, I get this. Okay. So this is the first part of the question. It just wants a formula written. And that's where your first mark comes from. Your second mark then, the second part is differentiating. And now we want to know what the speed is when it was half its maximum. Now we proved up in part 2. Oh, what happened here? So that's part 2. That's part 3. And this is part 4. Okay, we proved up here in part 2 that it had a maximum speed at NA, and we want to know what is the particle speed when it's half its maximum. Okay, so let's find out what time that occurs to start with. So when it's half its maximum would be NA. We don't want to know when it's equal to that. We want to know when it's half of that. So dividing it by 2 or timesing it by half. So now I'm just going to solve this for t. Now, hence find the first time the particle speed is half its maximum. Okay, yes, so we're solving this for t. Straight away, I'm going to divide this an over here. I've got, if I write out the whole thing, so my NAs are going to cancel, and I'm going to be left with just 1 on 2. So therefore cos of nt equals a half. Now solving this, thinking about our triangles, I'm going to get that nt equals pi on 3. Solving again for t, so t equals pi on 3n. And there's my solution. Tough question. Okay, so this was asked in 2009's HSC. It was question 5, but this is when they only had 7 questions in the HSC, so it's definitely at the back of the paper. It's tough just because it had no numbers in it. It's all in terms of the formulas and proofs. So that's why I wanted to show you this one, because if you do get one very similar but with numbers involved, you know what you're doing. The most important thing is simple harmonic motion is this stuff here. Okay, so if you can know that stuff well and have an understanding of it, you're going to be fine with the questions.